ירין עובד עם וולקן.
אני זוכר, הוא גם הגיע לפה ולקוליקילום אחד, לא? אוקיי.
זה היה, מי שהגיע זה עידו.
ירין מה?
ירין שני מאיר. הוא למד איתי תואר ראשון.
לא...
ואז הוא עזב, ואנחנו ביחד עם מור רוזנר מהטכניון. אם אתם מכירים אותה, כי כאילו, היא מדברת הרבה בכנסים.
אני לא הבנתי. איפה זה יהיה?
בוויצמן.
בוויצמן?
אנחנו 3 מארגנים שהיה הצבעה, 2 מול 1, הם רצו ויצמן. אותי לא שאלו.
מה הם רצו טכניון?
לא, הם רצו ויצמן, כי שנה שעברה היה בטכניון. ולירין קל כי זה ויצמן.
לא, ויצמן נחמד שם, הייתי יוצא להיות שם.
לא הייתי בוויצמן אף פעם, אני...
הייתי להיות שם, אני מחלקה שם נחמדה.
וואי, יש לך זמן גם לתרגל, גם לזה, גם...
אם אני מוצא משהו.
הכנס בסוף אוגוסט, מה יש לך?
בסדר, אבל זה לארגן הרבה דברים.
לא, אנחנו די מאורגנים, זה כנס שדי... זה כנס שדי...
אתה לא מתרגל סמסטר ב'?
לא.
הבנתי. נכון, סיפרת לי, את סמסטר ב' מתמקד במחקר. אתה מסתכל בארגון כנסים, אבל כן.
לא, אני אגיד לך מה, זה כנס שהוא די...
מאורגן?
אנחנו די יודעים מה לעשות. וגם יש לנו את מור שהיא ארגנה אותו שנה שעברה.
בסדר. מגניב.
כן, כן. יהיה בסדר, איך הולך לכם?
בסדר, אתה יודע.
יופי.
כן.
טוב שככה.
אני עכשיו צריך...
לא שמעתי? מה אתה אומר?
מה, אני אומר, אני עכשיו משלים הרבה חומרים, כי פספסתי הרבה בגלל צהר.
טוב, כל
בסדר.
הרווחת דברים
אני
אחרים.
רצה לפגוע בך יותר. כן, כן.
הרווחת דברים אחרים.
לא יודע איך חכה שתיפול בסיבוב.
תשתה.
מה, 2? איך הוא יפול ב2?
תתפלא.
סיפור.
אפשר ליפול בסיבוב.
בשתיים.
אפשר.
שתיים מעבירים את כולם.
לא.
רק אחד אפשר.
לא, גם בשתיים אפשר.
אני באמת נותן שם.
לא, יאללה, תעשה לנו תקדים.
לא, זה לא תקדים, אבל אתה תהיה מהבודדים שנפלו בשתיים.
לא, אני מכיר אנשים שנפלו בשתיים.
כן, כן, אם אתה פשוט משקר להם. אם אתה משקר להם, אתה נופל שם. כאילו, אתה יודע, אתה אומר להם, בחיים לא נגעתי בסמים כשבאו שאתה עכשיו נסתו, אז כאילו... אז אתה תיפול.
שיהיה בריא. אתה יודע שדוד שלי יש לו בעיה עם פוליגרף, זה תמיד מוציא אותו שקרא.
אז הוא לא יכול לעשות סיווג אחד.
הוא תת-אלוף.
לא קשור, אתה יכול להיות תת-אלוף בלי סיווג בכלל, בטח בלי סיווג אחד.
אני לא יודע.
זה תלוי איזה יחידה אתה.
לא יודע, הוא נראה לי במקום... כאילו אני לא יודע מה הוא עושה, הוא גם לא יכול לומר לי מה הוא עושה.
זה עדיין לא אומר סיווג אחד. רוב צהל עם סיווג אחד.
אנחנו מפרגנים מה שיש.
אני לא יודע.
כן.
אני רק יודע... לא, אני רק יודע
Those
שניסו לעשות לו כאילו פוליגרף בצהל וזה לא עבד, ואז כאילו... צריך להסביר להם
Like this
שכאילו...
one, I guess.
לא, אבל-
This table.
אני אגיד לך מה, זה לא
this
מספיק
is
בגלל
not right.
שאתם תמיד מתחילים את הפוליגרף
אבל היא גם מעטה.
כן, לא.
ואם שם אתה כבר נופל, אז כאילו מבין שאין מה פוליגרף.
כן, זה מה שהיה. אז הוא
כלומר, זה לא שיפיל אותך
הוא עשה תהליך הרבה יותר ארוך, אני לא יודע מה הוא עשה.
שקר.
כאילו, שואלים אותו איך קוראים לו, וזה יוצא שהוא משקר, כן. הוא אומר על נקודה, זהו.
לא שואלים אותו, לא, אני קוראים לך ככה, פוליגרף זה תמיד כן.
כן.
תמיד כן.
לא, אתה יודע, זה כאילו שואלים אותו, האם קוראים לך ככה?
אז מה איתך?
It will take, but
גם טוב.
it's in a long while that you just have to skip the whole and
לא סתם,
yeah. Well, no wishes for the registration to shut up.
בסדר, עוד כמה דקות תהיה חמישה.
I assume. I haven't checked. I believe it's about to make.
האמת שאני שמח לסיים קורס, כאילו כבר די נמאס לי. לא על זה דיברתי על איך שאני מתרגל, אבל דווקא עכשיו נחמד לי בחלקיקים.
באמת? זה נראה לא מרוצה כאילו...
לא,
ספציפית עכשיו מכל הסמסטר
כל הסמסטר לא אהבתי כלום. ההרצאה היחידה שנהניתי זה ההרצאה הקודמת.
באמת? זה כרגע לא מרוצה.
ממש
הקודמת
לא.
הייתה מטורפת, כן.
הקודמת נהניתי מאוד.
הקודמת גם אני נהניתי מאוד, לא היית פה.
אבל היה...
מה הייתי פה?
לא היית בקודמת.
לא, בקודמת
הייתי
הוא היה,
בקודמת.
בקודמת
אתה שוכח עם ה...
אז שם הייתי הכי
Structure
מעורבת.
coefficient.
נכון, בהצעה הייתי הכי מעורבת.
253.
No, in here it was.
זה כאילו זה ההרצאה היחידה שקניתי בקורס.
I mean,
לא, הייתה
well,
מאוד טובה, אבל אני מאוד נהניתי כל
תגיד,
it's
זה
not
שונה
well explained.
Well,
זה לא כן.
It's an Thompson well
אתה יודע,
explained.
קיבלתי?
So he's not teaching from
אני
this
יודע
book.
אופק. משהו
Yeah.
באמת.
אופק עשה הכל.
קצת בזכות ירדן הוא אמר לי מה כדאי לי להשלים והשלמתי.
כן.
באמת?
כן, לא יודע, אופרטורי סולם וכאלה.
זהו, ואז הגעת עם...
אופרטורי סולם
וגורדון
רגע,
קרא
אופק אמר
לי
לך-
שמעת on the go.
אופק
כן,
אמר
גם
לך-
אני. עשיתי כבר 2 ולמדתי on the go.
אופק אמר לו מה להשלים?
מה? לא, אני אמרתי לו
לא,
מה
אמר לי
להשלים
מה
את
זה
זה, כאילו,
כדי
פיסה לו את הפינה.
לא הבנתי.
כי ידעתי מה אופק מלמד.
לא, כי אופק היה מטריל.
שאלתי אותו מה הוא יודע.
אם היית שואל את אופק מה אתה צריך להשלים, הוא אמר לך שום דבר.
זה ארוך מאופק, ארוך.
אומר לך, זה מי קואפישנט.
במקום של...
גם אנליטית הייתה ממש.
תשמע את הפרוגרפיה הזאת.
כן.
יפה לי, אני תמיד שלי.
לא, אתה ממש טוב בזה בהקדמה.
גם זה גם.
וואו.
I don't know if he knows.
מה שלומך?
כאילו, אני מבינה את הכל.
הקורס עצמו לדעתי נהדר. אני מאוד נהנה.
One of these ones will be.
אנליטי?
אני אומר.
Just turn down the.
קשה, קשה מאוד.
כאילו, לא, אין לו...
הוא לא מחזיק כמה מחשבה את כל ההרצאה.
Shalom. Good morning, everybody. How are you?
Well, fine, how are you?
Not very good.
Okay.
Not very good. But always it's a problem.
תקשיב, השאלה הזאת עם המדיטה החיצונית, זה מה זה פרפש? מה זה הדבר הזה?
A nice
כאילו, אם אתה נותן
Yes.
זה לא... לא, זה לא אפשרי, זה יוצא לי...
Hey, חברים.
זה יוצא...
How do I turn off the...
turn off the. Maybe somewhere from somewhere here.
Yeah, how do you turn this off? What?
There is enough.
ראיתי את התשובות בדרייב.
There might be a button somewhere on top here. I don't see
Did you get in the church?
No, there's no.
No, that's fine.
No, it's okay.
Yes.
We're starting. I was surprised. I thought there would be more students coming now. Last week of the semester, etc. So we're going to start the last and final section of this, again, shorter than usual semester. So hopefully, I managed to, the things we did not touch upon, I hope you don't feel they're missing. If you don't feel there's anything missing, that means I did a good job. Okay, so a quick recap. So last time we spoke about QED, QCD. Any questions? I don't want to go over the entire last lecture because I want to do a new thing. Any questions on the things we said? There was one question which I was asked, and I deserve I promise to give an answer. When we spoke about QCD and I introduced the Gelman matrices, I said this is a specific representation. And in that representation, of course, and there are the 8 Gelman matrices. They are I'm sure that you've seen that. They resemble very much the Pauli spin matrices, but of course there are more of them. There are 8, there are 3 by 3, so they're not the same, but there are a lot of similarities which can be used to derive Pauli properties. And you're asked to do that as part of your homework. And I mentioned that in this specific representation, the RGB take the simple form, right? R is just it's vector 1, 0, 0, G would be 0, 1, 0, P would be 0, 0, 1. I was asked how do you represent in that the anti-R, and the answer is simple, right? This belongs to a different space, so this will be a row vector, not a column vector. And the same for the other anti-particles. Okay. So today we're going to start the last thing, which I think is crucial to to know when you're studying particle physics, which is the brute Englert-Higgs mechanism, or short Higgs. The brute Englert-Higgs mechanism, which is pretty much built upon what we said last time. But again, any questions about the things we said already before we start? Yes.
We had a dynamic factor in the Lagrangian where we had a P minus all the things with the gluons.
Yeah.
And in quantum electrodynamics, it was minus A.
Yeah.
Minus IA.
What was that?
It was
You mean the symmetry that we had?
Yeah.
The symmetry group? Yes.
Yeah. So if they are both exist, so it has to be some factor that has that adds the momentum and the IA and the IGs.
I mean, you're in the framework of unified theory?
Yeah.
Grand unified theory. Yes.
And for a quark, there will be a photonic field and a gluonic field.
In that framework, yes.
Is there an interaction between photons and gluons? I mean, there shouldn't be, but,
No, there shouldn't be, not that I know of.
but they could. With
You mean mathematically?
Yeah.
That's $1 million question. Why is this symmetry group the way it is? Right? We are talking about SU3 for the quarks. There are theories in which it will be SU5 and that would include other terms.
Mhm.
We don't see that in nature. Why we don't see them in nature? I don't know. Maybe this is related to what we're going to discuss today and on Thursday about this spontaneous symmetry breaking. So that means that if this is correct, all these good theory, grand unified theories, that means that we are looking at a low energy range. And if we increase the energy to high enough energies, then maybe we will see these symmetries. That's part of the reason why people try to achieve higher and higher energies, to see if there are bigger symmetry groups and maybe new interactions that will appear there, and we don't see them. But, you know, this is Mother Nature.
Prediction
Mother Nature, there's no prediction.
to how big we need to go.
Well, yes, there is a good. There is grand unified theory. There is a good scale, which is the Planck scale. There is a natural one scale of energy. We discussed that, I think, in the first lecture. It's a Planck scale. This is the only natural energy scale that there is, basically. If we go to that energy, maybe we'll see new symmetries that are broken somehow.
How much it was?
10 to the 28 electron volts.
10 to the 3.
So,
Yeah.
a lot. Anyway, okay, so we're going to speak about the brute Englert-Higgs. Of course, they all got the Nobel Prize. They shared the Nobel Prize together.
In 2012.
I don't remember the exact year that they shared it. So, we discussed QED, right? We discussed which is responsible for electromagnetic interaction. We discussed a little bit QCD. We said that the gauge bosons are QED and QCD, photons and gluons are massless. As opposed to that, we know that when we speak about the weak interaction, the gauge bosons, which are the W's and the Z, they do carry mass. So that means that something needs to be changed. So we said introduction maybe. So one is that Z 0 and W plus minus have masses. That's done experimentally. Though, by the way, when this model was given, it was not known experimentally. They were only discovered 20 years later. Another problem which we did not really discuss is that the left-handed and right-handed fermions have different charges for the weak or isospin hypercharge. It's not something which we discussed. That means that the fermion masses would also break the gauge symmetry. Yes.
When you say left and right, you mean like with you use homework, like the 1 plus gamma phi, gamma phi,
Yeah,
or
the
something
handle
like
is
that.
it's the same. So I would say that
And they assumed in the theory that they are massless or have mass before they
the
discovered.
fermions have mass.
No.
No, this was not assumed. It was not known.
But they assumed they have mass or didn't have mass because
Yes, that was assumption because it was needed to explain why the weak interaction is weak. Okay, so fermion masses break down symmetry. Masses break gauge symmetry. You can see that I gave a small historical background. These problems are noted in 1961 by Sheldon Glashow. He was the one that wrote the first electroweak theory. And then in 1964, where the Groth, Englert, and Higgs came up with a suggested solution. Now, the reason why it's named after Higgs is because the Higgs, when he came up with the solution, he predicted the existence of a new particle, which is the Higgs particle, obviously. All right. Now, the idea of a hidden symmetry or broken symmetry. In fact, this idea is not so new to physics, right? We have many cases in physics where there are symmetries, but we don't necessarily see them. Okay? For example, right, the Newton's law of gravity is completely symmetrical, meaning we'd expect all planets to be exactly spherical. Right? Because the force that acts on any location is the same. Right? But of course, Earth is not symmetrical. We have mountains, we have oceans, and it's not exactly symmetrical. If you look from a distance, it is symmetrical, but when you look closely, it is not. So something breaks this symmetry, in a sense, right? Same you can say for Coulomb's law, right? Coulomb's law is responsible for the structure for electromagnetic forces, electric forces in between molecules. But when you look at crystals, right, if you go below a certain temperature, the molecules will be solidify and you get some sort of crystals, and some of the symmetry will be broken. Right? Coulomb's law is also completely spherical symmetry. So there is something, if you go to low enough temperatures or to low enough energies, there is something in nature that breaks symmetry. Okay? So the idea is not that new. Right. So examples in nature, despite the fact that the basic forces are symmetric, we hardly see symmetric structures. When I say symmetric, I mean fully symmetric. For example, e.g., Coulomb's law is responsible for the structure of solids. But we don't see, or we barely see spherical solids in nature. Right, so there is something else there. The same I said about the Earth. If we go back to what we're talking about, right? We're talking about the Lagrangian to describe the system. And although the Lagrangian is symmetric, often in the ground state, there is something that breaks the symmetry. Okay? Here, although the Lagrangian is symmetric, often in the ground states symmetry is broken.
How is that possible?
You see,
The Lagrangian describes the symmetry of the system.
the Lagrangian describes the system.
Yeah. So also the symmetries.
It does not have to be symmetric. I'm going to see that. Often when we look at the symmetries, we're looking at excited states, not at states that are in the ground state. If you know magnets, right, Curie temperature, right? Above a Curie temperature, the spins are aligned randomly. Below it, they will align in a certain direction, right? So something breaks the symmetry there. Okay, now just as a reminder, since we are dealing with QFT, and although we discussed that extensively in the last few weeks, I'll still put a short reminder of what we're talking about, just to make sure that we're all aligned. In QFT, a scalar field, phi. Right. One is a function of space and time. Right. That obeys some equation of motion. Obeys an equation of motion, such as well, it's a scalar, so it will be a Klein-Gordon field, for example. This equation has a trivial solution. Which is what?
0.
Yeah. Y equal to 0. This solution, how do we call it?
Back.
Yeah. This solution is the ground state. Has the lowest energy. Now comes the difference, right? In the realm of quantum field theory, what this trivial solution means that there are no particles, so we call it a vacuum state, right? In this state, there are no particles. And we call it the vacuum state. Question, Walter?
What does mean a trivial solution to a field?
What?
What does mean a trivial solution to a field?
Phi equal to 0.
Phi equal to 0, what is the input?
It's again,
Field.
phi is a field, right?
Okay.
Which obeys some equation of motion. You can write down an equation of motion for this field.
Okay.
This could be Klein-Gordon equation. Now we can solve the Klein-Gordon equation.
Phi is a function, right?
Phi is a function of space and time.
Okay, so we get 4 coordinates. X, Y, Z. What
What is the
phi
input
is a
for phi?
function of x, y, and z. Right?
Okay.
Phi is a scalar. It's a scalar.
Okay.
Think of a temperature, right? In any location of this in this room,
And trivial
Like-
solution
it's
is
equal
a-
to 0.
Yes, the solution to that is just a set of things that.
No, not a set. It's the field phi.
Okay.
Again, think of a temperature, right? You're mixing between the value of the function and the input to the function. Okay? The input to the function is the location. In every location in this room, I can put a thermometer and tell you what is the temperature. Temperature is a scalar value which can change between this point and this point. I mean, in theory, this point can have a different temperature than this one, but the temperature is a scalar. It's still a scalar. It's a scalar which depends on
Yes.
the location. Now I can say I have a solution which is t equal to 0 everywhere, phi equal to 0 everywhere. It's a trivial solution. It's not an interesting solution.
Okay, that's what.
Yeah, and this is what's called a vacuum state.
מצלמה לא עובדת. בשביל זה באתי.
עכשיו באים. Now, this solution is not the interesting solution. Right? We are now looking at more interesting solutions, which is around this solution we can use basically a perturbation theory, right? Basically exciting the state, right? Now, the first excited state, we call it particle, right? Around this solution, we use perturbation theory. Okay. The first quantum excited state represent one particle. With specific momentum. Second excited, the two particles, etc.
So it must be an eigenvalue of the momentum operator.
Yes.
Eigenvector.
Yes. Of this equation, yes. Okay, now I'm going to add up a new conditions. If you could, so this is the general picture which is true in quantum field theory. When you learn quantum field theory, I told you that you see the picture. Now it's just technical details which you can handle quite easily. Yes.
מה אתה אומר בפרטורביישן טוב? אתה מדבר על זה?
תורת ההפרעות. Small perturbation. You're learning perturbation quantum mechanics. Yeah.
What is the first quantum state? What about a state with one particle with a different momentum?
It's fine. You can have, you can do a perturbation theory. Okay, that we need to get into quantum field theory. Basically, when you're perturbing something, you're determining the momentum. You can have an excitation with a different momentum. There's an infinite number because it's like an infinite chain, basically. Okay. So yes, you have infinite numbers of first excited state. But the correct, the way to think of it is you have one excited state with a given momentum. Okay, now, so this is all QFT given in a few lines. Now I'm going to add up the following. The first thing I'm going to end up is self-interaction. Right, so add up the following. One, self-interaction term to the Lagrangian. What does it mean physically? If we're saying such a term, what does it mean physically? Semi? No, it doesn't mean that there are more than a single particle. Every field represents a particle. So it's the same field. I did not add up.
It's not a free particle.
Yeah, it's not a free particle. So that means that the particle is not free. Or is self-interacting. Interacting. It can interact with itself. Now we have a situation where the potential does respect the initial symmetry, but the ground state breaks the symmetry. While the potential respects the symmetry, its ground state breaks it. I'm going to see immediately what it means. Okay, well, I'm actually going to tell you what it means. This is going to give to mass. This is going to lead to mass terms. This will lead to mass terms of the particles, and plus theoretical predictions that can be tested. Theoretical testable predictions. Okay. It is there. Sort of.
What do you mean testable prediction?
Testable means something which we can actually test.
There are things here we can test. Or what does it mean?
No, this, okay, you're going to see that shortly. This will be answered either at the end of today or on Thursday. Yes?
הכוונה בפוטנציאל פשוט חלקי עושה אינטראקציה שהוא לא חופשי.
Yeah, we're going to see that. Okay, let's move on and then we'll see. Yes.
לא ברור לי, אבל כאילו למה החלקיק לא יכול להיות חופשי?
תכף אתה תראה את זה. זו אותה שאלה, תכף, everything will get clear. Okay, so we're going to start with a simple example, which is not part of the standard model Lagrangian, but is part of, for demonstration purposes. So let's look at the symmetry breaking. Breaking for real scalar field. So we have a scalar field phi, and let's look at the potential, which looks something like V of phi is half mu squared phi squared. That also far makes sense, but we're now going to add a new term, which is 1/4 lambda phi to the 4. The potential doesn't have to be harmonic number.
Okay.
Right? If I didn't have that, this will represent what? Right, the mass. Right?
So the Lagrangian L, right? 1/2 d mu phi minus v of phi. So this is 1/2 b mu phi.
Phi is the coordinate or phi is the field?
The field. Real scalar field phi. That's the question. Minus 1/2 mu squared phi squared minus 1/4 lambda phi to the 4. That's a Lagrangian. What is that? Kinetic term, right? So this is the kinetic term.
The Lamperian
D. What is that? That's a mass, right? This is V, so it's associated with the mass. And what is that?
Perturbation.
Right. That's a self-interaction term, right? So you can think of that as of a 4 vertex. Phi, and 1/4 lambda. So if you ask why, then you didn't understand anything we said at the beginning. Right? This is what it means, this term. We have a self-interaction term of the field phi with itself.
And if it was the third term, it will be.
Yeah, but I don't have a third term.
Okay.
What is the vacuum state?
Phi equals 0.
Right, and this corresponds to what? To?
0 Lagrangian.
If I look at the potential,
0.
this will be the minimum of the potential. Vacuum state. Minimum of V. Right? Now,
Phi is real.
yeah, it's a real scalar field. Where's the minimum of V?
Around 0.
Is it?
You want more intensity?
Right, yeah, well, we have two options here, right? Option number 1 is
0.
what? When is it 0?
And also at the plus minus root of mu squared
So,
divided by lambda.
So again, so
This will be
the
maximum.
potential has a minimum, right? The potential
Two maximums.
has a minimum. What is the requirement for the potential to have a minimum?
Second derivative.
Derivative 0 and second derivative positive.
Lambda greater than 0. Right? If lambda is smaller than 0, then the potential will not have a minimum. Right? We just go to the minus
Minimum
infinity.
and maximum.
Right?
Will have a minimum.
Now we have two options. Right? So option number 1. What is the first option?
The first equal to 0.
Are you not with me? What's the option? Mu squared is greater than 0. Then if I have to plot the potential as a function of phi, it will look something like that.
Mu squared can be negative? No. It can be
Phi is a
that's
real,
lambda?
but when lambda is not.
And then the minimum. So where is the vacuum state?
Phi equals 0.
Right, so right, this is the minimum, right? So the vacuum phi equal to 0. That's the minimum of the potential. That's what they used to. Right? And the Lagrangian will represent what you think of it is, right? Scalar potential with mass mu and some self-interaction term, as we call it here. But there is a second option. What is the second option?
Lambda negative. Oh, to
Lambda
that.
negative, we won't have a minimum. Equal.
U squared.
What?
Square is negative.
Mu squared is negative. What happens if mu squared is negative?
It's going to be a maximum.
What? First, that means that we can no longer say that half mu squared represents a mass term, right? Cannot be. It doesn't make sense. How does the potential look like?
Go below.
Right.
minimum.
Right. So now. This is how the potential, right? You agree? Where is the minimum? The potential?
Well,
Square divided by
Right, this is minus v plus v.
mu
So minimum.
Mu divided by.
Phi as minimum. That's phi is equal plus minus v, which is plus minus or minus mu squared over lambda.
You have to absolute value.
Yeah, they put absolute, maybe not one. Right.
Like square root is on everything.
So where is the lowest energy state?
Square root is on everything, not on the mu.
What? Other thing. Right. Where is the minimum? No longer at phi equal to 0. Now the minimum is that we have two minimum, right? Plus minus v. Now what if we start with the high energy? So let's say that the field in the ground state has a non-zero expectation value. So in the low energy, in the lowest energy, the field phi has a non-zero expectation value. What does it mean? Exactly that. The minimum of phi is not at 0. Right. Now, what about the symmetry of the Lagrangian? This is symmetric with respect to exchange between phi and minus phi.
An odd function. Is an even function.
Yeah, the Lagrangian is symmetric with exchange between phi and minus phi. There is no question here, right? But what happens in reality? The vacuum state is either here or here. The Lagrangian is symmetric, but in reality the vacuum will be only in one of these two. Right? So the choice of which state the vacuum will be, right, this is what breaks the symmetry of the Lagrangian. This is known as, this is spontaneous symmetry breaking. Right? So, while the Lagrangian is symmetric with respect to exchange phi minus phi, the vacuum state can be either plus phi or minus phi. And so breaks the symmetry down as spontaneous symmetry breaking. Yeah.
It feels a little bit unphysical conditions. You define this mu to be some sort of mass term, and
I did not say it's some sort of master. You're very wrong.
Okay.
I said I have a potential.
Okay.
Right now, the potential I can have a quadratic term, right? And if mu was positive, then you say, okay, I'm relaxed because I know how to interpret this quadratic term. And I'm adding another term with phi to the 4, right? And you're still okay with that, right? You don't have any problem with that because the potential doesn't have to be parabolic potential, right? Now I say, well, I'm assuming that mu is greater than 0 because then I know how to interpret it easily. Right? And I say, okay, this is the mass. But mathematically speaking, it doesn't have to be like that. Right?
Yeah.
It can be negative. And it still fulfills the basic condition that the potential will have a minimum rather than a maximum. But this doesn't depend on that. But if this is the case, then yes, I can no longer interpret mu as a mass term. It is not. Right? I don't know what is the interpretation right now.
Why cases like that appear?
Why nature is like that?
No.
This is how nature works, you know.
Well,
I'm describing to you the mechanism. This is how it works. Why it is like that? It works. I said, right? I even wrote it.
Okay.
There are testable predictions to everything I said. Has been tested. Higgs will not get the Nobel Prize just for a nice mathematical idea. Right? The Nobel Prize, you get the Nobel Prize if you give a prediction and the prediction is turned out to be correct.
Mathematician
And
don't have
important.
any Nobel Prize.
Right. Again, I gave the example of a ferromagnet, right? In a ferromagnet, it works exactly like that. Right? You have all the spins are randomly oriented and then you start cooling down. When you reach the Curie temperature, they all suddenly are getting aligned in one direction or the other direction, right? Which is exactly what we have here, right? When you're here, that they are everywhere, but when you're lowering the potential, essentially, they will select where to go in a spontaneous way. So this is not something which is never seen before in physics. Okay? Yeah. Okay, let's move on. Yeah.
אם אתה מוריד את הפוטנציאל בין 0 לפוטנציאל המינימלי, אז אתה רואה שיש לך 4 פתרונות. שזה חושב פיזיקלי?
In reality, no. The field will choose where to be either here or here. Let's do it now. The point here, right? If mu happens to be mu squared, happens to be smaller than 0. Remember, it's just a number. I could call it just mu. I call it mu squared. I feel happy with that. I could call it whichever name I want, right? But it can be anything, right? Once it drops down, then the field will spontaneously select where to go, left or right. Now let's see what happens. So without loss of generality, let's assume that phi is going to the right. So phi is equal to plus b. So assume for now that the vacuum state is phi equal plus b. Right, but this is not interesting. This is the vacuum, right? We are interested about particles, and for particles we need to excite the field. Let's make an excitation of the field. So the excite the field. Around the ground state. So that means perturb around the ground state. And we get that phi is equal to V plus eta of x, some parameter. So again, V is constant, it's not changing, right? This is the minimum of the potential, right? But phi itself can be a function of x, and also eta is a function of x. Right, you're all with me?
X, you mean the 3-vector or the 4-vector?
Yeah, well, this is a simple example, right? It would be a 4-vector here, but this is really like a one-dimensional example. So it doesn't really matter. Again, this is not the real Lagrangian in the standard model. This is for demonstration. Before we develop the full Lagrangian, that you get the idea. Yeah.
השדה שלך בעצם הוא סביב נקודת
The perturbation is around this point, yes. I'm perturbing around here, not around 0. So, I'm putting in the Lagrangian, which I wrote and erased. So now I can write the Lagrangian in terms of eta. So Lagrangian will be written as 1/2. Since V is constant, then the d mu will really be d mu of eta, right? So it will be a d mu eta minus 1/2 mu squared. Now we have phi squared, so I'm just going to write V plus eta squared minus 1/4 lambda V plus eta to the 4. I just wrote down the same Lagrangian, but instead of phi, I plug in V plus eta. Right? I care about the perturbation around the vacuum state. We said the minimum of the potential minimum is mu squared is minus lambda V squared. Potential minima. And when we plug that in here, we end up with the following. The Lagrangian will be 1/2 d mu eta. Now, minus lambda V squared. Okay, I'm just going to write it down all the terms, and then you'll just expand them up at home and see that I got it right. Minus lambda V squared eta squared minus lambda V eta cube minus 1/4 lambda eta to the 4 plus 1/4 lambda V to the 4. This is just algebra. Just plug it in, expand, and that's what you're supposed to get.
You can throw out the 4th and 3rd.
I am not throwing out anything. This is exact. Did not throw out anything.
That is okay.
Now, we have a term that, so we have now a kinetic term. Now we wrote the Lagrangian as a function of eta rather than of phi, right? Now we have a kinetic term for eta. So we have a quadratic term in eta, which will be a what? What will be the interpretation? Yeah, this will be the mass term. So we can write down that this is the mass term. So we have m eta is square root of 2 lambda V squared, but lambda V squared is minus mu squared, so this is square root of minus 2 mu squared. So this Lagrangian, and of course all these will be interaction terms, right? eta cube and eta to the 4. No, this is constant, so the eta to the 4 is here. Right? So, what do we get now? We get a massive, this Lagrangian now that we have here represents a what? A particle with a massive scalar field, right? So, so this Lagrangian, the Lagrangian represents a massive scalar field.
What does mean massive scalar?
Okay. So we say, because this can now be interpreted as a mass. So we said that the mass was discovered by the symmetry breaking. Right? So created. So the mass was created or discovered by the symmetry breaking. Yeah. I just wrote down the Lagrangian. Fine. I just made a perturbation around the ground state. Just wrote down the same Lagrangian that I had before. That's all.
זה לא ברור, אבל לא הבנתי מהביטוי ללגרנגיאן, נתת את...
I have a term which is quadratic in eta squared. Now it's a Lagrangian is written as a function of eta rather than of phi. Right? So now I have this extra mass term which has the right sign. Yeah.
First, you said the particle excited has a specific momentum. What is this particle's momentum?
This one would not correspond to that because we did not quantize it.
Okay.
This is within quantum field theory. I did not quantize it.
And you said in the perturbation theory if we can find the first excited term, we can find one particle and two particles. So how
We can find as many particles as you want.
How can you find the
Wait. We'll get to that. I'm not sure if we'll get to that. So skip that to the break. Right now, let's focus on that. Okay, the point I'm trying to make here is that by the spontaneous symmetry breaking, we retrieve back a mass term. Okay. And again, I mark for myself, right, that the particle got the mass by being close to the vacuum, right, excitation from the vacuum. And it's very similar if you know about solitons. It's the same thing, right? What? Sorry, phonons, not solitons. Phonons. My mistake. You know about phonons?
Yes.
Yeah, okay. So they obtain an effective mass exactly because they are close to a parabolic potential.
Yeah.
So again, it's the same analogy. Now we still have two terms here. One is, we have three terms. This is just a constant term. So we have eta cube and eta 4. Right? So they would be identified as a what?
Self-interaction.
Yeah, self-interactions. So eta cube, I'll just write it as 3 etas. Eta, and the strength of the interaction is lambda v. And eta to the 4, the strength of the interaction, eta is 1/4 lambda. So again, this is the same Lagrangian that we had before for phi. Okay? We just now write it, not with a perturbation around the the new vacuum state. All right. Can we move on? Good. So, this was a real scalar field. But nature is a little bit more complicated than that. Let's look at the global symmetry breaking of a complex scalar field. So if we have a complex scalar field, then we can write it down. Phi is complex field, so I'm just going to write this 1 over square root of 2. Phi 1 plus I feed phi 2. Phi 1 and phi 2? Real fields. So the corresponding Lagrangian, L, is not going to be phi 1, phi 2, real fields. The Lagrangian d mu phi star d mu phi minus mu squared phi star phi minus lambda phi star phi squared. Everybody's happy with that? And again, what's the requirement for the Lagrangian to have a finite minimum? Lambda greater than 0, right? Lambda greater than 0. This is a physical requirement.
Shouldn't you have a half instead of the mu squared so it will be a master, or you can interpret it?
Yeah, wait. Not interpreting it yet.
Again, why lambda has to be?
What happens if lambda is negative? What happens to the potential? We'll go to infinity, will go to minus infinity, right? So it's going to be a minimum. Well, it's going to be a finite minimum. Okay.
You need
So-
to have the global minimum. Why?
Now, this Lagrangian is invariant under global U1 phase transformation. Invariant L, invariant under U1 global phase transformation. Right? Which is what? Phi goes to phi prime, which is equal to what? E I alpha phi. Right? Global alpha is not depending on space or time. It's everywhere the same. Yeah? That means that what? Phi prime star, phi prime is equal to what? Phi star phi. So obviously the Lagrangian is invariant. Now again, you have two options. Option number one is that mu squared is greater than 0.
Why spontaneous phase can happen?
Why what?
Spontaneous phase can happen.
It's a spontaneous phase. I said this Lagrangian is invariant under U1 global phase transition.
Yes. Okay.
That's what I said. So if mu squared is greater than 0, which is what we used to, where is the minimum of the potential?
0.
There, right? So if I plot down, now it's going to be a bit more tricky, right? Phi 1, phi 2, and it's going to be a V of phi. It's going to look like some sort of something like that. Can you see? Roughly. You get the idea. It's not a particular. What if mu squared is smaller than 0, get like so how many minima do we have?
No,
What?
infinite.
Infinite, right? So the potential. So if mu squared is smaller than 0, then if I plot phi 1, phi 2, and this will be v of phi, it will look something like that. Right, something of that. Excuse me for my symmetry. Right? You have all these set of minima around here.
This surface is all minimum points.
Everything that I plotted in purple. Circle, right? This is the location of all the minima. Right? Why? So what's the definition of the set of minima? Yeah, of course, but mathematically.
The radius
So,
in color
minima.
is,
Minima
Is equal to the value equal to
2 phi star phi. What is 2 phi star phi? If I write phi as phi 1 plus I phi 2. Very good. Phi 1 squared plus phi 2 squared is equal to minus mu squared over lambda, which I call v squared. Yeah?
לעשות את המעבר האחרון.
you put
להפסיק 1 בריבוע ופי 2 בריבוע שווה בריבוע.
It's the minimum point. The same thing here. Phi star phi minus 2 times minus mu squared over lambda. And just plug it in here, phi star phi, and calculate what it is. Yeah, I'm trying to plot the 3D, the potential. It's a potential. This is a 0, right? And this is how the potential looks like, and then it's like a circle, right? It's around. The minimum, no, the minimum is the purple circle. It's like a sombrero, right? A sombrero. It's cool, isn't it? It's getting nicer and nicer.
Phi 1 is real and phi 2 is the image, right?
No, phi 1 and phi 2 are both real fields. Just
Yes,
phi is a complex scalar field.
Okay.
And I wrote it as phi 1 and phi 2. That's
Okay,
it.
okay.
Both phi 1 and phi 2 are real fields.
Yes.
Yeah? Good. Now, what is the physical vacuum state? Right. Yeah, go on. So the physical vacuum state is some arbitrary choice, one point on that circle. Right? And what does it mean, that selection of one point?
symmetry.
It's breaking the U1 global symmetry. Now where am I heading, if you can see? Because this is not going to represent the real, what happens in reality. What will be the next step? Local symmetry, right? What will be the local symmetry? What we just saw, right? The gauge field. But one step at a time, we'll get there. We'll get there, right? So this is a U1 global symmetry, right? So selection of vacuum state is equal to breaking U1 global symmetry. So again, without loss of generality, let us make such a selection. Right, so I'm going to select a point, which will be on the real axis, just because it's easier for me. Okay, so I can write down, so choose a vacuum state. Right, which will be now phi1, phi2 is v and 0. Yeah, it's our arbitrary choice. Okay, so I'm going to be in the real plane. And what am I going to do? Exactly what I just did for the real field. So I'm going to expand around the vacuum state. Expand around the vacuum. Right? What does it mean expand around the vacuum? That means I'm going to write down phi1 of x is a v plus eta of x. And phi2 of x is a 0 plus, let's say, psi of x. That means that phi of x, I'm going to write as 1 over square root of 2 v plus eta of x plus I psi of x. Yeah, you're still all with me? The algebra looks slightly more complicated, but the idea is the same idea. So, what is eta here? What type? That's a radial perturbation, right? So a perturbation around here. And psi?
The
It's
movement
imaginary
of the circle.
perturbation, right? Perturbation along the circle. And so we now have phi star phi is 1/2 v plus eta squared plus psi squared, and mu squared is a minus lambda v squared. So the Lagrangian, which is written here, I'm going to write it as, let's move on here. L, again, it's the same L, right? I'm just going to is 1/2 d mu eta plus 1/2 d mu psi minus lambda v squared eta squared minus v interaction of eta and psi. For v interaction of eta and psi is minus 1/4 lambda v to the 4 plus lambda v eta cube plus 1/4 lambda eta to the 4 plus 1/4 lambda psi to the 4 plus lambda v eta psi squared plus 1/2 lambda eta squared psi squared. That's just by plugging it in here and expanding. Nothing too fancy. So, I have one quadratic term in eta, which is of course this term. What's the interpretation? Mass, right? So again, so we said that the eta particle has a mass. So 1/2 m eta squared is lambda v squared. What about psi? It's massless. Because we're moving in the direction where the potential is not changing. Right? Eta moves in the direction where the potential increases. right? Psi moves in a direction where the potential is the same. Right? So it's a massless. So psi, massless. Right, so this is excitation. This corresponds to excitation in the direction in which V potential does not change. So we end up with a massless scalar field, and this massless scalar field has a name. It's called the Goldstone boson. This is known as Goldstone boson. Not surprising, right? After Goldstone. Yes.
So massless particles just go near the on the circle of the minimum.
Particles don't go anywhere. We have an interpretation. I assumed I put the Lagrangian of the field. I just said, look, what happens if the Lagrangian have this strange shape? I put a minus sign at the beginning. Then I said, okay, I have an excitation. So then first the vacuum state is not at 0. The vacuum state is somewhere else. Now I'm saying, okay, if this is the vacuum state, let's see what does it mean that I'm making some excitations. So if I make an excitation in the direction where the potential changes, I get something which I can interpret as a particle, which has a mass. It's that mass. And if I make an excitation in the direction where the potential is steady, I'll interpret this as a field, which I can interpret as a particle, but it is massless. It doesn't have any mass. So the theory gives rise to one massive particle and one massless particle by exciting the vacuum state, which I got there after spontaneous symmetry breaking of the potential. Okay? Potential is symmetric.
So in real field, we can't have a massless particle?
In real field, I didn't have it, right? Just had a one-dimensional, basically. Okay. Now, okay, any further questions? Now we can start talking about the Brute-Englert-Higgs mechanism, or the Higgs mechanism in short. Can I erase that?
Yeah.
Can I erase that? Yeah?
That it will not change.
What?
What does it mean that it will not change?
Potential is not changing in this direction.
Okay.
Okay. I already tell you. Yes, question.
Is there the physical, like real system Lagrangian are holomorphic functions?
What do you mean by holomorphic functions?
Maybe I'm using the wrong term, but כאילו גזירות במובן המורכב.
Is Cauchy Riemann
Yes, it's continuous functions.
But they have derivatives, but in any direction. But you need to be like in the complex number term, meaning.
I think intuitively I would say the answer is yes, but I didn't really check it.
This example wasn't.
Why not?
Because the
you mean because I have a different particles there? Maybe. Okay, I don't know. I did not think of that. No, the Lagrangian itself is continuous symmetry, but it's not. Spontaneously broken Lagrangians would still be holomorphic? I don't know. I have to check. I don't know. I don't know often the answer to it. Okay. Now we can go to start discussing the Brute-Engler Higgs mechanism, or what is known as the Higgs mechanism for short. So we have the same thing. What's the difference? So we have a spontaneous symmetry breaking. Of a complex scalar field. Right? Is the potential we apply the same way that we had. U squared phi squared plus lambda phi to the 4. Now, spontaneous symmetry breaking of what? Local gauge symmetry, right? Spontaneous symmetry breaking, now it's going to be symmetry breaking of a local gauge. Symmetry. So the simplest example is the U1 local transformation. Again, this is still not the standard model, but we're getting there, like one step at a time. Excuse me. G. Local U1 transformation. Phi of x goes to phi prime of x is e to the I g chi of phi, chi of x, excuse me, phi of x. What is g? Coupling constant, correct? And the charge of phi is 1, and we don't care about it right now.
Can be also negative 1, right?
What? Coupling constant?
No.
What? The charge? Yeah, depending on the difference charge. Right now we don't care about that. So, what does it mean? How do we make a Lagrangian invariant under local? You get the term, right? The term to what? The derivative, right? So we must add the term to the derivative. So for the Lagrangian to be invariant under local gauge transformation, we replace the derivative with the covariant derivative. D mu is replaced by capital D mu, which is D mu plus I G V mu. And V mu, what is that? It's a local, what? What is V mu? It's a local gauge field, right? A new gauge field, V mu. Gauge field. What do we know about this B mu? The transformation law, right? So B mu, gauge field, transforms as B mu goes to B mu prime, which is B mu minus D mu chi. exactly as we did for the Dirac-Lagrangian. Right? It's identical. The requirement for a local gauge invariance here implies that there must be a new gauge field, which we know what the transformation properties of this field. So now the combined Lagrangian. So the combined Lagrangian combine of the complex scalar field and of the gauge field V would be complex scalar field phi plus V plus gauge field V L is minus 1/4 f mu nu, beware it's not the same f, plus d mu phi star d mu phi minus mu squared phi squared minus lambda phi to the 4th. F mu nu, what is F mu nu?
Electromagnetic.
No.
Mu
This is the kinetic term of the gauge field B. Right. Is d mu v nu minus d mu v nu, kinetic term for the gauge field. Now we know that this gauge field has to be massless field, right? Because if it was massive, it would break the symmetry of the Lagrangian. So, okay?
No, why it has to be massless? Why if it was massive, it will be
It will not be a gauge invariant.
Okay.
It's the same thing we did
Okay.
before.
Last
time, right?
Okay.
The same thing we did for QED. Yeah.
איפה רואים את האינטראקציה בין בין ואיפה האיבר של האינטראקציה?
You were not here last week? You were? I was here last week, right? Okay. So, okay. So, we do now, again, so we're now combining what we did last week with what we did earlier, right? We're just now proceeding, okay, this is, we got from last week, identical.
Yeah.
Now we do what we're doing, we proceed as we did earlier with the global gauge, right? So, for mu squared smaller than 0, we have a symmetry break. Which means that since the vacuum state is generated, once we select a specific vacuum state, we break this degeneracy. Okay. So again, we choose the vacuum state, symmetry, symmetry break, vacuum state is degenerated, degenerated. So choosing a vacuum state. It's choosing a physical state breaks this symmetry. Then, okay. Okay, so we select like we did previously. So we choose phi 1 and phi 2 to be and 0. And again, we expand the complex scalar field. Expand around the 0. So we can write down 5x 1 over the square root of 2. Exactly what we did. V plus eta of x plus psi of x. And I'm putting that inside this Lagrangian. So use that in here. And we get that the Lagrangian now will become slightly a bit more lengthy, but it will be 1/2 d mu eta minus lambda v squared eta squared, that's the mass term, plus 1/2 d mu psi that's the psi field, the Goldstone boson, minus 1/4 f mu nu, plus the interaction terms, plus 1/2 g squared v squared b mu minus the interaction plus g v b mu xi. And the interaction, which is of eta sine b, that will contain all sorts of 3 and 4 point interactions. Of the fields of eta sine. So I don't care about them at the moment. What's these first two terms?
Kinetic and mass?
Yeah. Of? No. What? Of eta, right? So this is a massive scalar field eta, right? Mass of the eta. Massive scalar field eta is 1/2 eta is lambda v squared. Again, similar that we had before, the mass comes from breaking the symmetry of the Lagrangian. That term? This is the? This is a massless what? Massless Goldstone boson. What are the next terms? This term and that term. What? This is the vector field, correct. This is the massive vector field. Right, so this term is for the vector field B, which was before it was a massless. But now we have this new term, which is the mass. So the vector field acquired mass. Right, 3 is a massive vector field. B mu. So the mass of B mu from here. So 1/2 mv is 1/2 g squared v squared. So again, where did this B came from? Yeah. Where did it come from? The covariant derivative, right? Requirement for a local transformation. So it comes from the local symmetry breaking, basically, right? Originates from local symmetry breaking. As opposed to the global symmetry. That is the Higgs mechanism, essentially. That's quite cool, what we got. That's not complete. That's not the end of the story. But we're halfway through. So let me just tell you what are the problems with that. So there are two main problems. One of them you may be able to see right away on the board. Right. What's the first problem? Yeah? Yeah, that's right. What is the last term?
Self-interactions.
No, it's not self-interaction, it's interaction. Interaction between what?
Field and
Between B and
Goldstone boson.
Sorry, between the Goldstone boson and the B field, right? But they cannot interact, right? One of them has spin 1, one of them has spin 0. Right?
Why does
Goldstone boson is a spin 0 scalar field because we started with a spin 0.
why is the fact that spin are different mean that they can interact?
They just don't. One is a vector field, one is a.
Ah.
Right. So the last term, 1, the term G, V, B mu, V mu psi represents.
The exponent of G.
What?
Is this multiplication G times V times B mu, or is it G to the power of V
No,
times
it's
B mu?
multiplication.
Oh, okay.
Y to the power of V. Represents direct coupling between psi and V, right? But V is a gauge field of spin 1 and the Goldstone is a scalar field. Scalar field is spin 0.
No, I still don't understand why they can't interact. I understand there are different things.
They
but
just don't interact. They don't have a often. Let me
why?
finish. The other thing which is more difficult to spot is the degrees of freedom. The original Lagrangian had 4 degrees of freedom. Think of them as 2 of the scalar field, phi 1 and phi 2, and 2 the polarization state for the massless gauge field B. Right. 2 for the field, for the scalar field. 2 scalar field. Phi 2 for the massless boson B. Massless gauge field. But when we acquire this mass term, right, that means that
Another degree.
right, somehow there's another degree of freedom which was added to the system. But when V acquired mass, a new degree of freedom was added, miraculously added. So there must be something wrong.
You're supposed to have mass.
What?
You're supposed to have mass.
I don't know, it will have mass. But the solution, by the way, is that the fields here are not physical fields. So there has to be something else there still. And I think it's a good time to stop and talk about this new addition on the last lecture on Thursday. Yeah?
כאילו אני מבין שנוצרה לו מסה ל-B, אבל למה אתה לא יכול לדעת את המסה מהאזור הזה שעשינו נכון, למה זה דרגת כל הנתונים אני יודע
אנחנו דיברנו על זה שהיה באחד השיעורים שיש לך פוטון למשל, מס באזור, יש לו שני דרגות רוקה. דיברנו על משפט רוקה למשל, במצב עליון יש לך עוד דרגת רוקה. מאסיב פילד.
אוקיי. ויש לי עוד שאלה, אולי הייתה טעות בשיעור הזה, היינו צריכים לעבוד שהאופרציה בליזרת ריבוע ניתנת ביחידה, גם להחלטה גודל 2 על 2, גם היה אמור לתת רבע כפול.
יכול להיות שיש לנו פקטור.
לפני 3 שקופיות בערך, ככה, עשית, חישבת גם ככה את המסה של אצה, אבל אני חושב שהשורש, שורש 2
לא, השורש זה ה-V בריבוע היה שורש של מיו בריבוע. מינוס V בריבוע.
אוקיי, סבבה. ולא הבנתי את החלק הזה, but when... המשפט הזה.
זה בדיוק השאלה שאני נשאלתי. היה לנו את זה לפני כמה שיעורים, דיברנו על זה שיש אוטון, יש שלו, חופש פנימיות, שקוראים לו כיתוב, יש תיק מסיבי, אז יש לו 3 דברים. אתה מקבל את שהכיתוב לא מיתודי, מה שאין לך בפתרון.
אני חושב בשיעור הראשון אתה אמרת שכאילו המודל הסטנדרטי לא חוזה את המסה.
הוא לא חוזה את המסה.
זה בגלל זה?
לא. המסות במודל לא קשור. המסות במודל הסטנדרטי הם פרמטרים חופשיים. אתה יודע איזה יהיה מסיבי, ואתה לא יודע להגיד מה המסה שלך.
פורסט כן, לא יכלת להגיד מה המסה שלו. הנה המסה של אתר.
איפה אני יודע מה זה V ומה זה ומיו ולמדה זה פרמטרים שאני שמתי כבר בעצם הגדרתי דיפרנציאל בצורה כזאת.
המצב ה-ground state, מה הוא יייצג לי? כלומר, אמרנו שבוואקום סטייט אין חלקיקים, ואז שאני מעורר יש חלקיקים. אתה לא יודע להציג לוואקום סטייט כאילו במצב של כאילו יש ככה, שיש מינימום מה שהם לא אפס.
לא, עדיין יצא כוואקום, אבל הוואקום הזה לא יהיה בפי שווה לאפס.
אוקיי, כאילו יהיה סוג של מעורר?
לא, סוג של מעורר. זה בדיוק הספונטניות סימטרי ברייק. יש לך יותר ממצב ואקום אחד.
אוקיי.
תחשוב על... הכי פשוט זה מה זה הקרי טמפרטור? טמפרטור קרי?
קריאטור קרי?
אתה לוקח איזשהו פרומגנט, הוא מספיק חם, אתה מחמם אותו מספיק, נכון? אז הספינים שלו יהיו רנדומיים. עכשיו אתה מתחיל לקרר אותו, בנוכחות של שדה מגנטי, אז הספינים יכולים להיות כולם, הם יבחרו או להיות בכיוון אחד או להיות בכיוון אחד, כולם ביחד. זה כל הרעיון, שיש לך יותר ממצב ואקום אחד. שאתה לא, משהו שם שובר את הסימטריה. אתה, עכשיו, מבחינה פיזיקלית, מבחינה אנרגטית, כל דבר זה זה. אתה לא יכול לדעת מראש שאתה מתחיל לקרר אם אתה תסיים בספינים אפ כולם או בספינים דאון. אבל אתה יודע שאתה תסיים באחד משני המצבים האלה. למה? כי ככה זה קורה.
עוד שאלה.
לא לומדים של כלום.
איפה אני רואה את הקווינטות?
פה אתה לא רואה, זה הקוונטום פילטר, אני לא מקוונטט לכם פה כי זה ייכנס לזה. אבל זה לא קשור לשאלה של הטן. בשביל זה אני צריך לקוונטט את זה. אני צריך להפוך את זה לאופרטורים שפועלים עליו, אני לא עושה את זה.
אבל ב-QFD,
QFD השדה יהפוך להיות
לא, אני סתם
אופרטור.
לא יודע שום דבר ואיכשהו מוצאים את השדה.
אני ארשום את השדה, אני אתן לך את זה רק בקליפה שתרגיש איך זה. כמו שבאוסצילטור הרמוני יש לך העלאה והורדה, A ודגר, נכון? אז אותו דבר בשדות, תרשום אותם בתור אוסף של אופרטורים, זה אינטגרל, כי זה שדה, אז הוא אין סופר, יש לך אינטגרל של אופרטורים של העלאה והורדה.
כן, כן.
פה אני לא עושה את זה, אני לא מפתת את זה.
כן, כאילו, אז לא תוכל לעשות את מה שעשית עם ה-V ועוד כאילו את ההפרעה הזאת. אבל בפועל אתה אומר שיש לך רק מצבים...
בסוף אני אהפוך את השדה הזה, אני אוכל לעשות אותו.
ועדיין הוא ייתן אנרגיות המשכי, כאילו... כי הרי אנחנו ראינו שזה...
לא, הוא לא ייתן אנרגיות, זה כן חלקיק. זה האינטרפטציה אחרת. באוסצילטור הרמוני, כשאתה מעלה רמה, אתה הגדלת את האנרגיה. פה, כשאני מעלה רמה, אני יצרתי חלקיק, זו אינטרפטציה אחרת לגמרי. אני פועל על הפקטור. תחשוב על דיראק C, זה אולי האנלוגיה הכי טובה. כך זה דיראק C, דיראק C. עכשיו אני רוצה לייצר אלקטרון, מה אני עושה? אני הולך לעידן שלי, אני שולף ממנו בחלקיק, אני שם אותו ברמה הזאת. מה זאת אומרת, עכשיו יש לי פה אלקטרון.
אז איפה השמה לרמה מסוימת, זה כמה נכנס לרציפות שראינו או ש... כן,
למה נכנס לאינטרפטציה? אני מציע לאינטרפטציה, אני אומר השדה פי. כאן אני כותב לגרנג'יאן שממנו אני כותב את משוואת התנועה, נכון? והמשוואה היא נכונה, אותה משוואת תנועה שתהיה בקוונטים ואם אני מפתת, זה בסדר גמור, אני לא מרמה אותך. יש לי פה לגרנג'יאן, ולגרנג'יאן אני גוזר את משוואת התנועה של השדה. אחר כך אני לוקח את השדה הזה ואני אומר, אני נותן לו פה אינטרפרטציה אחרת. עכשיו השדה הזה, אני לא מתייחס אליו בתור משהו קלאסי. אני תמיד נותן לכם פה את הדוגמה הקלאסית. עכשיו יש לי מתחום ביד, ואני יכול להגדיר את שדה הטמפרטורה. יש לי פה מגנומטר, אני יכול לבדוק איפה התקדמות לשדה המטבע, אז אני אגדיר את זה כיוון כל נקודה בקוונטום פילטר, אני אקח את השדה הזה ואני אגיד, עכשיו השדה הזה הוא בעצם אופרטור. עכשיו אני לא אומר לכם את זה, אני לא עושה את זה, זה לא קורס בקוונטום. בסדר? השדה הזה עכשיו, אני עכשיו משחק עם השדה הזה, אני אומר מה קורה כשהשדה הזה הוא... הוא עדיין יפתור את המשוואה הזאת, גם בשדה האופרטור יפתור את אותה משוואה. זה בסדר, לא משנה פה שום דבר. האינטרפרטציה תהיה אחרת. אני רק אומר לכם מה האינטרפרטציה של מה שאני עושה.
שאלה שונה, בסוף אנחנו נראה ש-B זה X.
זה משהו אחר.
איך אנחנו יודעים שבביטוי הזה יש מסה ובביטוי הזה אין מסה?
זה האיבר הזה.
ואיך אנחנו...
ברגע שיש לי איבר קוודרטי עם אטה בריבוע, או אם היה לי פה איבר אלכסאי בריבוע, אז זה אינטרפרטציה.
כאן אנחנו עושים כאילו כאן יש איבר עם V בריבוע ו-G בריבוע. אוקיי, איך אנחנו יודעים שזה כאן מסה עבור ה...
זה אינטרפרטציה. ברגע שיש לי פה את הביבר, מה זה? B זה קבוע. קצת לא קבעתי את זה, זה משהו שהוא קבוע, לא נוגע בו. הדברים הדינמיים שלי פה זה פסאי, אטה ו-B. זה פשוט מספר מבחינתי.
אז ברגע שאנחנו רואים איבר של אטה או פסאי או B בריבוע, אז אנחנו יודעים שיש מסה. זה אינטרפרטציה. מאיפה זה מגיע האינטרפרטציה הזאת? זה משהו שראינו אותו בהרצאות קודמות?
של נניח דירה של קליין ורמונות. תמיד יהיה לי איבר שנראה אין בריבוע פיבולרי.
אוקיי, ואז הפי בריבוע זה מסמן את המסה.
זה בעצם מסמן את המסה.
אוקיי.
בסדר?
כן, אבל נפש אסף, שאלה. כתבת בקירוב בסביב טוש. כתבת פי של x שווה 1 חלקי שורש 2 v פלוס את ה-x פלוס i אבל הדבר הזה בסביבת הנקודת מינימום לא חוזר להיות V, זה חוזר להיות V חלקי שורש 2. זה אמור להיות...
יש לי שם 2 שם איפשהו.
ואז...
V סקוואר V זה יהיה חצי...
אוקיי, זה נספר פעמיים ואז זה נוסף?
לא נספר פעמיים. החצי כי בהגדרה שם יש לך שם מינוס מיו בריבוע חלקי 2.
אוקיי, יש חצי כבר מראש. אוקיי, סבבה. אוקיי, בסדר. טוב, אני עכשיו צריך להשלים, יש לי עוד הרבה חומרים.
יש עוד הרבה ואני גם קצת אפילו עוד התקדמות בינתיים.
כן,
אני
פשוט עכשיו משלים הרבה כי לא הייתי בסמסטר ואני צברתי פער בכל הקורסים בגלל זה לא היה לי מה לעשות, זה צהל הזמין אותי והייתי צריך להיות שם. תודה רבה.